My name is TOMASZ, and I'm glad to tell you today about math programming and maybe about implementation is in Ruby. So let's start. I would want to start with telling you a couple words about myself. So I work as a Ruby on Rails tech lead in the company called SoftSwiss. We are working in the iGambling industry, and I'm also a PhD candidate. So I'm currently working on some stuff related to drones. Besides that, I'm interested in things like the cloud computing, linear programming, and financial markets, and of course, everything related with the software engineering. So let's start with the formal definition of the math programming. So math programming or math optimization is a systematic approach used for optimizing the value of an objective function with respect to a set of constraints. Or maybe we can simplify that and say that it's just the attempt of defining our specific problem using the math equations and some elements like the decision variables, constraints, objective functions, and other stuff just to receive the best solution possible. So how does it look like? So in order to define our problem, we need to use several types of the elements. First of all are the parameters. So in general, all of the numbers like this one or this three that cannot be changed during the program execution and are constant before we run our software can be called the parameters. We need to define our decision variables. A decision variable is the thing that is unknown for us, so we want to determine its value, and it's our goal of running the software. We need to have our constraints that will set the values of the decision variables. So we need to somehow limit the possibilities and give additional conditions. For example, we have a condition that the sum of two variables needs to be less or equal to 10. And we have the objective and the problem. So objective is the value that we are caring about. We want to either minimize or maximize it. So in our case, the problem is the maximization. So we're trying to maximize our objective. That's simply the x1 in our case. And giving the constraints from the previous slide, x1 plus x2 is less or equal to 10. We have one line there, and we have two other constraints as horizontal and vertical lines. So the graph shows all the solutions possible for our equations, but of course we don't want to take just any of them. We want to select best possible for our case. So our objective is x1 and we are maximizing it. So we want to select the solution with the highest x1 value. That is the x1 equals to 7 and x2 equals to 3. Yeah, but of course not all problems are so easy, and the whole strategy can be used in the real life, in the big corporations. So there is a company called Groby that's the leader in the math programming software, linear optimization, and they are working with some big high-tech companies. So, for example, they are working with the Air France, and the similar strategies allow the Air France to create flight schedules to save some money on fuel or minimize delays. Math programming is used for the Copenhagen airport for assigning the check-ins, for Audi to optimize the supply chain, or for Lufthansa to plan the usage of simulators. There's just a couple of use cases because there are like hundreds of examples, so if somebody is really interested, I'll recommend visiting their page and seeing it. Yeah. The problems can be split into 4 most important classes. So first 2 types are the linear programming problems. The first type includes only variables that are linear, so we don't want to have just the integer values, but for example some decimals, etc. And we can introduce the constraint that we want just integers, but it increases our complexity. And there are also the quadratic programming with the integers, but it's more advanced and complicated stuff. So we'll just care about the linear programming today. The whole problem is related to the P versus NP computer science problem. So in all of the computer science algorithms, there are 2 separate classes P that are the problems possible to solve within the polynomial time, and NP, the problems with the higher complexity. The scientists are unable to prove that the subset P and P are not the same, but currently we are unable to provide any polynomial solution for the NP, so we are assuming that they are not equal. So our LP linear programming is in the P class that's easily solvable, and we want such kinds of the problems. And our mixed integer linear programming, so that includes the integer variables, are unfortunately in NP, and it's very hard to solve in some cases and takes a lot of computer resources. Yeah, so we can be afraid of solving some of them even if there are just like 20 variables, because it can impact the computation time significantly, even if it seems like the easy problem. Okay, so how to implement it with Ruby as we are on the Ruby conference. So we need 2 parts. First part is a solver that is like a black box software. We will provide some predefined problem for the solver, and it will return the best solution for us. And we need to somehow communicate our solver with the Ruby software. So we need the library gem that will be used as a wrapper between the Ruby and the solver, or we need specialized modeling language like IMPL, but it's more complicated and it's rarely used with Python or Ruby, so we'll use gem in our case. So let's go to the solvers. So when you want to select a solver, there are several classes. We'll focus on licensing. The commercial ones are more often much faster and need less resources to solve the same issue, but unfortunately they are very pricey. So we'll use the open source one as we want to save some money. So we'll use the high solver, and there are some another like CBC that are slower, but in most basic cases we'll be probably fine with any of them. There is a graph of the performance of some most commonly used solvers. It's maybe not most recent information, but it's still kind of valid. So the commercial solvers are both faster, and what's more important, on the horizontal line there is a number of the solved problems. So the more problems you have solved, it's better. So if you're using the non-commercial solver, you'll be unable to solve some issues, some instances and models, and when using the commercial one, you'll be good to go in most cases. In that case, in 86 of 87. So there are 2 most popular games for Ruby, Ruby CBC, that is only suitable for the CBC solver and does not allow to use any other solution, and the RULP, that stands for Ruby Linear Programming. So RULP is probably the most comprehensive solution for Ruby, for linear programming currently, and you can use some heretic approaches. For example, you can use JRuby or PyCal to integrate with the commercial libraries or libraries like Python's Pulp that are widely used in the scientific approaches, but we'll focus on Ruby native approach. So let's go with RULP, as in our case it does not really matter, in fact, as we have quite easy problems to solve. Okay, so RULP is a Ruby DSL for the linear optimization. It supports multiple solvers like CBC, commercial ones like Groby, or in our case like Heis, and it uses the LP problem format for describing the problem. So if you ever use it and you want to migrate it to the commercial stack, it won't be a problem, as the LP format is like the battle tested, so you can migrate your code without any issues very quickly, easily. And there is no vendor lock-in, so you can integrate any solver you want or any solver you need within minutes. For example, I implemented Heis from the scratch in like 2 hours 1 month ago, so it's very efficient if you need to add some functionality. Yeah, there are some Ruby DSL commands and statements that we'll use in defining our problems. So as to define the variable, you need to use the capital letter at first and the proper suffix. The suffix determines the type of the variable. So if you want to integer one, you just have a suffix, and for Boolean variable is b, etc. We need to select proper objective type. So we want either to minimize or maximize our problem, and we need to set our objective when defining the problem. Constraints are possible to be defined after the problem type is set, and we just need to select a solver that will be used for finding the best solution. So it's done by setting the proper environment variable. We can skip the solver output, or we can show everything by setting the log level, and we're good to go. So we can solve our problem, see results, or we can just check the value of each individual variable one by one. Yeah, so I have a simple demo to start. So we have just a few lines of the code. We selected a proper solver, log level. So our problem is quite basic. We have just objective with 2 variables. We are adding x1 to doubled x2, and we decided that the sum of the variables needs to be equal to 10, and all variables should be non-negative. So we're gonna solve it and see if the result is correct. Yeah, so we got x2 equal to 10 and x1 equal to 0. That is correct, as we can see that by adding a value to the x1, we will increase the objective value much faster than by increasing the x1. So, but there can be some other results of our problem. If we defined it correctly, it's optimal, like in the previous case. but there can be some issues with our formal definition, so it can be infeasible when we have some constraints that are conflicting, that are unsolvable at the same time, or it can be unbounded when we have not enough constraints, so it can be improved indefinitely, and we want to avoid such situations. So, for example, now the sum of the x1 and x2 that are both the integers needs to equal 10, but we are adding another constraint, so currently they need to be equal both 10 and 5 at the same time, and it's not possible as 10 does not equal 5. So let's try. Yeah, and we got the solve-failed invisible result, and we can comment out both of the constraints. So currently we are maximizing such equation, and there are just two constraints that both of the x's needs to be positive. So we can increase them infinitely, and it will still be compliant with all of the constraints. So when you try to solve it, it returns the error that the problem is infeasible or unbounded. So in our case, it's unbounded. So let's try to solve something more complicated. So let's start with the knapsack problem. So we have a backpack that has limited capacity. In our case, it's 15 kilograms. And we have several objects. Each of them uses our backpack capacity, but gives us some profit. And we want to select as many items as possible just to maximize our earnings. But we can see that we are not able to choose all of them, as they will exceed our backpack capacity. So how can we solve it? Okay, so we have the set of the items, and we need to define 3 arrays. First one will be the parameters defining the weight of each item. The second one, C, is the profit for each item, and the last parameter is the knapsack capacity. The only decision variables will be defining is if the item is selected or not, and we want to make sure that our weight of selected items won't exceed the backpack capacity. So when the item is not selected, the x will equal to 0, so the component will be equal to 0 and won't add anything to sum. And if the item is selected, it will add the weight of the selected item. And we want to maximize the total profit. So like the previous one, it will add only the profit from the items that were selected and packed into our backpack. So let's try it. So we have a Ruby code. So we defined the variable z, that is the backpack capacity. We have the array j, that's just indices for writing a simple code for our case. We have w, that's the weight of the items, and we have c, that defines the profit of getting the item to the backpack. So we define the 5 decision variables, so the size of the indices array, and we are defining our constraint and objective. So our constraint is that the sum of the weights shouldn't exceed the backpack capacity, and our objective is the sum of the total profits of the items taken into backpack. So let's execute it and see if it works. So the result is that we should take all of the items except the item with the weight of 12 kilograms and the profit of 4 USD. So let's see how it looks. And so if we'll choose all of the items except the green one, we'll get 15 USD profit and 8 kilograms. So we are not be able to collect the green item. So it seems it worked and there is no better solution. Okay, so finally we have some real-life problem that can be utilized in the production application. So we have a public transportation system and we want to find a route from the point A to the point B. And our goal is to get to the point B in the shortest time possible. We need to simplify it a little bit as we have a limited data source. So we'll ignore all of the changes in the vehicle routes and we'll ignore all of the delays. And we are focusing only on the shortest possible time of arrival. So we don't care if there is a direct connection or we'll need to have 2 transfers. We just care about arriving as quick as possible. So there are some existing solutions. The Polish market, there is the app called Jak dojadę, but there is also the Google Maps functionality. So if you search for any destination in Malmo now, you'll probably get some instructions how to get there by bus, and the Google Maps under hood searched for the route by you, so for you. So it did the similar thing we want to do right now. Okay, so that's how the simplified graph of the public transport look like. So we have several stops that are marked with the letters, for example, A, B, C, D. We have the several lines that are marked with numbers. So we have the line number 2, line number 1, or line number 3. And we have the departure times from the stops. So the line number 2 departs from the stop E at the time 12 and 22. So we want, for example, to find the shortest route from the stop C to E by taking any number of transfers. Okay, so we got a real data set. So I found the timetable on the website of the Polish city called Słupsk, and they have like the mid-size public transport system. There is 172 stops, 18 lines, and more than 1,000 daily courses of our lines. I've scraped only weekdays just to simplify our problem, but it wouldn't be much harder to include all of the Saturdays and Sundays. That's how it looks like. So it's mostly included in the city center, but there are some single stops at the suburbs, and we'll try to model it and find the best routes between some of the stops. Okay, so I will not torture you by reading all of this. I will just go quickly and describe the sense of the solution. So we defined the set that includes the stops and the rides. We have the parameters like the time when the bus is on the given stop and the information about the passenger's journey. So we want to know when the journey starts and when the journey ends. And we need to determine when the passenger needs to go out from the given ride, or when the passenger needs to take the following ride just to arrive to the final destination. And we define 5 constraints. So most of them are mostly responsible for making sure you are taking one ride after another, that you are not able to do some crazy stuff like taking 2 rides at the same time or time traveling. And we need to make sure we arrived at the final destination and that our journey started after the passenger came to the first stop. And our main goal is to minimize the time when the passenger arrives to the final stop. So we just care about the arrival time of the vehicles, and we are selecting the vehicle that is arriving to the final stop and that is selected by our passenger. So all of the components of these sums will be equal to 0, except the one that is selected by the passenger. So that represents the decision variable here, and we are minimizing our objective. So let's try how it works. And so we have like 100 lines of the code. So we are parsing the user input just to get the name of the first and destination stops. We want to get the arrival time, and we are defining some constraints to provide the valid route. After the problem is solved, we are just checking which of the routes was selected to go into and when the passenger took off from the vehicle, and we are displaying the results on the console. Okay, so here we have a sample route between 2 stops at 6:50 a.m. So we are loading all the information. There are like 5 megabytes of the data, and we are trying to find the best route. So the software already found it. We are departing at 6:52 a.m. and we are taking just 2 transfers. So we are arriving at 7:26 a.m. and it's the best possible solution according to our model. It took like 4 seconds to solve. Okay, so let's compare it with the commercial application that is built by the company specializing in such things. So our model in the previous case returned the similar transfers, and we've arrived at 7:26 a.m. and the commercial solution suggests arriving at 7:23. In another case, we are trying to travel between the same stops, but in our case, we are getting, unfortunately, a very long journey, 3 hours instead of a half hour. Yeah. So I wondered why did it happen, as it does not look correct, at least. Okay, so there are some reasons. First of all, we have just the official timetable from the city website, and it did not include some routes, some transfers, but the app Jak included everything, as it was based on the historical data and they got the live updates. we didn't take into possibility that we can just walk to another nearby stop, like 200 meters, and just have the transfer there. And we were not able to adjust travel data based on online updates. So that's mainly why we got 3 minutes later, as the official application was aware of the current traffic, etc. And in this case, we just didn't have information about some additional courses when there was a high demand for the public transportation. But unfortunately, such an approach has some drawbacks. So, first of all, it has a very long calculation time. It may not have looked like it took so long, but if the city is much bigger, it can take several minutes, or in the worst case, when I tried to investigate the whole Warsaw, it took 1 hour. So it's unsolvable for the big cities without any simplification. We need to update our information about the rides online, so we would need to have another data source, but it would require to update our model constantly, so it would increase our complexity even more, and we won't be able to predict any unforeseen situation without constant model changes. But there are also some ways to at least slightly improve our model and make our approach more usable on the production. So first of all, we can reject some other far parts of the city that we are not interested in when making sure that the path is the closest. So we don't want to travel 30 kilometers if we want just to take another stop that is 1 kilometer from us. We can aggregate some stops if they have all the lines the same. So it's not possible to take a transfer, or at least it does not have any sense. And we can split our problem to sub-problems. For example, we can make some of our stops a hubs when we will make transfers and estimate the shortest possible way from our first stop to the first hub, and calculate the way between the hubs itself using our model. But of course, it's maybe just not the best solution for the given problem. I just gave it for the scientific and learning purposes, as it may be a good approach for some real cases, but maybe the public transportation system is just not the best example for doing it. So we'll need to think twice before we'll decide on the specific approach. Okay, so what's about the production? So first, we need to discover if there are some other better solutions. For example, in our case, it may be a graph algorithm. It may be much faster and give some results. We may be able to limit some execution time by decreasing the quality of the result. We can use the math programming for the tasks when we don't need to have an instant response. So for example, if we can calculate something and we just need it in a couple days, we can do some background calculation, and after 1 hour we will be guaranteed to have the best response possible. And there may be some non-trivial problems that would require some complicated algorithms if we want to implement them by ourselves in a Ruby code, but otherwise we can just use the math programming, define them, and solve them using the specialized software, and we will get rid of some sophisticated algorithms written by ourselves. Yeah, and that's it. So if you have any questions, I'll be glad to answer them. Thank you.
Thank you very much, Tomasz.